Salam and welcome everyone. So today I am just compiling a bunch of shorter videos for my channel for any student who is reviewing your physical chemistry for an exam or for a test. The goal of this video is for you to review the examples that I've done already on this channel from the physical chemistry Atkins textbook. It is to help you in your journey through physical chemistry, whether you're about to take a test or whether you're doing a bunch of problem set. I wish you guys all the very best. Please enjoy the video. And today we're going to be working on a compression and molar volume of a gas question that says a gas at 250 K and 15 atmosphere has a molar volume 12% smaller than the calculated one from the perfect gas law. Calculate one, the compression factor under these conditions, and two, the molar volume of the gas, which are in the sample the attractive or the repulsive forces. So this question is kind of intertwined. We're supposed to find compression factor, we're supposed to find the molar volume of the gas, and we're supposed to find whether is the attractive forces that are dominating the sample or the repulsive forces that are dominating in the sample. So you have three different questions in one question. So the first thing you have to do is, of course, write down the information that you're given. We know that the temperature is 250 Kelvin. We know that pressure is 15 atmosphere. We know that the molar volume, right, of the molar volume is smaller than that calculated from the perfect gas law. So the molar volume of the real gas is the same thing as 12% less than the perfect gas law. So it's the same thing as saying the molar volume is going to be 88% of the molar volume that you get from the perfect gas law. So we don't know what this is because they're giving us information in percent, and it's also actually what we're supposed to solve. We're supposed to find the molar volume of the real gas, the compression factor, which is Z, and usually the compression factor formula is this one right here, the molar volume of the real gas, okay, divided by the molar volume of the ideal or perfect gas. So that is what the compression factor is. So let's go on to what we know. We know that the perfect gas law is PV equals nRT. We're not given the number of moles because we're told to find the molar volume. So instead, we're going to make this formula into the proper formula whenever you're given molar volume. So you just divide both sides by n, right? And you cancel out n here. And what you end up with is PVM, which is molar volume, because molar volume is just the volume divided by the number of moles. So I hope this is like you have actually have an understanding, because here we're not looking for number of moles, we're not looking for volume, we're actually looking for molar volume in and of itself. So we have to make sure our formula is in that form. So we have that divided by RT. Well, we've been given our pressure, our temperature, we know the gas constant. So we have the molar volume VM is the same thing as RT divided by P. So we start to substitute. Gas constant, same thing as 0.08206 dm cubed atmosphere divided by mole Kelvin, that's the unit, times the temperature, which we're given to be 250 Kelvin, and then divided by the pressure, which we know to be 15 atmospheres. Cancel out the atmospheres. Let me use blue. Cancel out the atmosphere, cancel out the Kelvins, which makes sense, right? dm cube is the unit for volume, mole is the unit of number of moles. So dm cube per mole is molar volumes unit, which is correct. So 0.08206 times 250 is the same thing as 20.515, okay, divided by 15 right here, dm cubed per mole. When you input this information in the calculator to solve for that, you just end up with 1.37 dm cubed per mole. So make sure you have your calculator handy because you need it whenever you're working with questions in thermodynamics or in physical chemistry. So this is it, 1.37. Now we have the ideal gas, or the one we got from the perfect gas law. Now we have to note that we're told that the molar volume of the gas is 12% smaller. So that means we're going to be looking for 12% of something is the same thing. 12% smaller or 12% less of something is the same thing as 88%, right? 88% of that thing. Do you understand what I'm saying? So for example, if we say, let me like explain this using X, okay? If I say something is 12% lesser of X, is me saying something is 88% of X. Do you get what I'm saying? So this X in this case is not an unknown. This X is what we just solved for, which is the molar volume that we solved of the perfect gas using the perfect gas law. So 12% smaller of this is the same thing as 88% of this. So when we go there, we're just going to have 88%, which is the same thing as saying 0.88 0.88 of 1.37 dm cubed per mole that we solved, which is for the perfect gas right here, is going to be what is the real gas, right? That we're actually solving for. So you just have to input this information to calculator and solve in 3-sig-fix. When you input that in the calculator, you're going to see that the molar volume of a real gas right here, because this one is for a perfect gas or an ideal gas right here, molar volume of a real gas is the same thing as 0.88 times 1.37, which when you solve it, you end up getting 1.206 dm cubed per mole. And when you do it in what you call it, when you do it in 3-sig-fix, you end up with molar volume of the real gas to be 1.21 dm cubed per mole. So that is it. We've solved the first part of the question. So the second part of the question now asks us to find the compression factor under these conditions. Well, we can see the compression factor is actually the first question, the molar volume is the second question, but you can find you actually end up finding the molar volume in this question before you can find the compression factor, if that makes any sense. Anyways, the compression factor under these conditions, well, we have Vm real divided by Vm ideal. So, your Vm perfect, whatever you want to call it. So we have compression factor Z is the same thing as the molar volume of the real gas, that value divided by the molar volume of the perfect gas or the ideal gas, whatever you want to call it. So you end up with 1.21 dm cubed, okay, divided by mole, divided by the value for the ideal, which is just 1.37 dm cubed per mole. So you cancel out dm cubed, cancel out mole. So you end up with Z equals 1.21 divided by 1.37. You put on your calculator to get 0.883. So I'm going to do this in 2-sig-fix, which is going to be approximately 0.88. You can see that this is the answer to the value of the compression factor. Now, the third part of the question, we want to know whether the sample is the attractive forces dominating or the other one, or is it repulsive forces that are dominating? Well, this is not hard. You just have to remember the concepts, right? Z less than 1 and Z greater than 1. When Z is less than 1, when the compression factor is less than 1, 0.88, like in this case, the attractive forces will dominate, right? They dominate in the sample. But in a situation where the when the compression factor Z is greater than 1, the repulsive forces dominate. So I'm only teaching you guys this. This is not what the question asked me to do. The question is asking me whether attractive forces dominate or not. The attractive forces are actually the ones dominating because the compression factor is 0.88 and the compression factor is less than 1. So since the compression factor is less than 1, the attractive forces will dominate. If you have another question, not this question, another question, where the compression factor Z is greater than 1, just know that the repulsive forces are the ones dominating. So hopefully that's very helpful. If you have any questions, please put it in the comment section. If you need extra help with your tutoring this semester and other semesters, make sure you email me at shuhabitutoring@gmail.com. Salam and welcome. So this is the second part of the compression factor molar volume question. If you've not watched the first one, it's already on my channel, so please try and watch that one. So this question says a gas at 350 Kelvin and 12 atmosphere has a molar volume 12% larger than that calculated from the perfect gas law. Calculate the compression factor under these conditions, and 2, molar volume of the gas, which are in the sample the dominating and the repulsive forces. So basically, they want you to find the compression factor, they want you to find the value of the molar volume, and they also want you to tell them or answer the question whether it's the attractive forces that is dominating in this sample of gas, or is it the repulsive forces that is dominating the sample of gas. So the first thing you do, like you do every other math question, is for you to write out the information given. We can see that the temperature we're given is 350 Kelvin. We can see that the pressure that we're given is 12 atmosphere, right? And we have a molar volume 12%. So 12% larger, so 12% greater, right, than the perfect gas law. So that means the molar volume of the gas is 12% greater than that of the molar volume of the ideal gas. So we're asked to find Z, which is the compression factor, and we're asked to find Vm, the molar volume of the real gas. So that is it. Well, since they told us that we're about the perfect gas law, the first thing we have to do is to find the molar volume using the perfect gas law, which is PV equals nRT. Well, we're not finding for the volume here. We're not trying to solve for the volume here. We're just solving for the molar volume, which is the same thing as saying the molar volume of something is the same thing as volume divided by number of moles. So we're now going to divide this information by number of moles, and we can cancel out number of nodes on the right side, and we can just have the V divided by N as having this new equation right here. So that's PVM equals RT. So the molar volume times the pressure equals RT. So this is how you basically get what you need in this question. So continuing it, since we have the temperature, we have the pressure, and we have the gas constant, we can rewrite this equation to what we actually supposed to solve for, which is the molar volume. So that would be Vm equals RT divided by P. That is how you get this. And yeah, that's how you get this. So let me erase all of this information here and just rewrite this. Vm is the same thing as RT over P. So yeah, let's substitute. We know the gas constant to be 0.08206, the units to be dm cubed, atm divided by mole Kelvin, times the temperature. We substitute that as 350 Kelvin. And then we have the pressure to be 12 atmospheres. So we cancel out the atmospheres and we cancel out the Kelvins. And we end up with molar volume equals 0.08206 times 350 divided by 12. This is equivalent to, when you put this in the calculation, you actually get 2.3934 dm cubed per mole, right? And pay attention to the units. We already said molar volume is the same thing as volume divided by number of moles. So the unit of molar volume is actually the unit of volume divided by the unit of mole. So dm cubed per mole is actually what you get. Now, we've gotten this information right here. Now we're asked to solve for the, what do you call it? We're going to solve for the molar volume of the real gas. And they say that is 12% greater. So this is the one for the ideal that we just solved here. Then the one for the real gas is what we're about to solve. So note this. When you're dealing with percentages and you hear something is a so percent greater than something else, is the same thing as saying now that if you have 100 of something, right, or 100% of something, right, this new information is greater by 12 more percent. So that would be 100 plus 12%. So that's actually going to be 112%. But since we're dealing with percentages, we have to remember that, say something like 5% is the same thing as 5 over 100. If you say something is 20%, same thing as 20 over 100. So when we get the decimal of this value, 112% is the same thing as 1.12. So going back to the question, we're told that the molar volume of the real gas is 12% larger. So that's just going to be 1.12 times whatever we got the molar volume of the ideal gas to be, is going to now give us the molar volume of the real gas. If that makes any sense, right? So that would be the molar volume of the real gas is going to be 1.12 times what we've solved, which is 2.3934 dm cubed per mole. You input that in your calculator. What you end up with is the molar volume of the real gas is going to be 2.6806 dm cubed per mole. When we do this in three significant figures, we end up with the molar volume of the real gas is approximately 2.68 dm cubed per mole. So that is the answer to this question. 2.68 dm cubed per mole. This is absolutely beautiful. Now, we are also told, now that we found the molar volume of the real gas, or the gas we're solving for, we're told to find the compression factor. I wanted you guys to know this, that compression factor is very, very important as you're learning when you're learning the real gases. You have to note that you would need to use a formula, and the compression factor formula are many, but in this particular question, the compression factor formula we're going to have is Z equals, okay, the molar volume of the real gas. Are you hearing? You listening? Divided by the molar volume of the ideal or the perfect gas. So you can call it perfect gas, you can call it ideal gas. That is just basically it. So now we have the information for the real gas, which is 2.6806 dm cubed per mole. And again, the notes that the Z value, the compression factor, has no units. It's just a number. So now divided by the molar volume of the ideal gas, we solve this. We saw that that's 2.3934 dm cubed per mole. Cancel out the units. So 2.6806 divided by 2.3934, we end up we having the real the compression factor to be 1.1199. So when you do the three sig figs of this, you're going to see the compression factor is actually 1.12. So that is the answer for this question. Compression factor here is 1.12. Now, we have to remember that the question also asks us a third one, which are in the sample. Is it the attractive forces or the repulsive forces that are dominating in the sample? Well, another thing you need to know about compression factor is this is just the general law. Whenever the compression factor is equal to 1, what you're dealing with is an ideal gas, basically, or approaches 1, whatever you want to call it. Whenever the compression factor is greater than 1, what you have to know is that the repulsive forces dominate. So you're going to have attractive and repulsive forces anytime you're dealing with a real gas. An ideal gas is just Z equals 1, right? There's no attractive force, there's no repulsive force. It's just basically it's like balance, if that makes any sense. Because I mean, it's an ideal gas. It's just the ideal gas explanation is just for us to have an understanding of thermodynamics. In the case of a real gas, understand that when Z is greater than 1, the repulsive forces dominate in the sample. Okay. When Z is less than 1, know that the attractive forces dominate. So in this particular case, we have 1.12, hence it is greater than 1. So the answer here is that the repulsive forces dominate. So hopefully this has like helped you guys. So yeah, if you have any questions, please comment it in the comment section, or sorry, write it in the comment section. Salam and welcome everyone. So today we're going to be working on the question on the screen that says, estimate the internal pressure of sulfur dioxide at 1.00 bar at and 298 kelvins, treating it as a van der Waals gas when internal pressure, so pi sub T equals A divided by Vm square. You may simplify the problem by assuming the molar volume can be predicted from the perfect gas equation. So this question requires us to find the value of the internal pressure of sulfur dioxide, so SO2, at 1 bar and 298 Kelvin. So the initial pressure and temperature is given. We're also told to treat it as a van der Waals gas when we use this equation. But in order for the problem to be simplified, we have to use the molar volume that we can predict from the perfect gas equation. So the first thing you have to do is remember that molar volume is basically a value you can get from the perfect gas equation. And to get that, you have PV equals nRT. Note that Vm is the same thing as volume divided by number of moles. So we have to write this perfect gas equation in terms of V divided by N. So to do that, what we end up getting is for you to just simply divide number of moles here, divide number of moles here. So what you end up is PVm is equal to RT. You can rewrite Vm is now going to be RT divided by P. So this is basically the formula that we're going to first of all use to determine the molar volume. We have to remember that looking back at the question, we've been told the pressure is 1.00 bar. Okay. We have been told the temperature is 298 kelvins. And also we've been told the internal pressure value to use, but that's just by the way. Now, of course, since this is a perfect gas equation, the gas constant R is constant, and we can use any of the two gas constant values depending on the units. So we're given pressure 1 bar and temperature 298 kelvins. I am going to be converting this 1 bar that we're given, to the proper units of atmosphere, because that is what I'm comfortable with the most. You can use bar, but just make sure that it matches the gas constant value that you'll be using to solve it. So 1.0 bar to atmosphere, we have to remember that 1 atmosphere is going to equal 1.01325 bar. So hence 1.00 bar would give you how many atmospheres. So let's just use the unknown value x. We're going to use the proportionality method to find the value of 1.00 bar in atmospheres. So this is just going to be x is going to equal 1 atmosphere bar, okay, just hold on with me, divided by 1.01325 bar. Of course, when you have similar units, you can cancel out numerator, denominator, so that 1 atmosphere divided by 1.01325. So that that pressure in terms of bar is going to be 0.97402 atmospheres. So this is the pressure in terms of atmospheres. So we have that pressure in terms of atmosphere. We have our temperature. We know the gas constant that we're using. We can just simply substitute. So Vm is equal to RT divided by P. So that would be 0.08206 dm cube atmosphere divided by mole Kelvin, okay, times the temperature. Looking back at our question, temperature is 298 kelvins. So that would be 298 kelvins divided by the pressure, which is just 0.97402 atmospheres. So of course you cancel out, sorry, this is not dm's, dm cubed. So of course we're going to cancel atmosphere, we cancel our atmosphere, we cancel our Kelvin, we cancel our Kelvin. So we end up with the molar volume is going to equal 0.08206 dm cubed per mole times 298 divided by 0.97402. We input all of this information in our calculator to get 25.106 dm cube per mole. Now, the next thing you have to do, of course, is for you to use the formula internal pressure. So pi sub t equals A divided by Vm squared. So that's how we're going to estimate the what's it called, the internal pressure. So pi sub t is equal to A divided by Vm squared. We have our Vm, we don't have our A, we have pi sub t. But remember what A is, right? A is just the strength of attractive forces for the van der Waals gas, right? In the particular container. So you have to note that the value for A is a constant and it's going to vary from gas molecule to gas molecule. So looking at the resource section of our book, we can find out what A is. So the research section of our book, which is just basically the book, this is a physical chemistry book. You can also Google it online. You can find the value there as well. So we have the A value to be 6.775 ATM, okay, DM6 divided by mole squared. So the strength of extractive forces for SO2 gas, sulfur dioxide gas, is 6.775 atmosphere, DM6 divided by mole squared. So now we have the value for A as well as the molar volume. We can just simply substitute to find the pi sub t. So pi sub t is now going to be 25.106 dm. Sorry, that's a mistake. We have the A value. I was writing the molar volume up top instead of it's being at the denominator. So the value, the A value is 6.775 atmosphere dm6, okay, divided by mole squared. All of that information divided by 25.106 dm cubed per mole. All of this information squared. So we have pi sub t equals 6.775 atmosphere dm6 divided by mole squared divided by 25.106 dm cube divided per mole. So that's just going to be, first of all, let's square this unit. So that's going to be dm cubed squared is the same thing as dm6. Mole squared is the same thing as just mole squared. So now 25.106 squared is actually 630.3181. So now we've basically squared the denominator. So of course we're going to do the main thing we do in chemistry. In calculations, we cancel out the units. So what you end up remaining is atmosphere, which makes sense since we're finding the internal pressure anyways. So the units have to match. So that would be pi sub t is equal to 6.775 atmosphere divided by 630.3181. So that's just going to be 0.010749 atmospheres. So yeah, that's basically how it's done. Now I want to mention something because we're not actually done. we have to go back to our question to see the least number of significant figures that we have in the question. You can see that 1.00 bar and 298 kelvins are the only numerical values, and they're both three sig figs. So we have to make sure we put our internal pressure final answer in three sig figs. So we're going to just approximate up until 7. So pi sub t, or the internal pressure, is actually 0.0107 atmospheres. So this is basically the answer to the question that we're given, 0.0107 atmospheres. So yeah, that's basically how it's done. If you have any questions, please put in the comment section. If you would like me to do more problems and do more questions in all STEM related courses, you could also put in a suggestion in the comment section. If you have any concerns or questions, put in the comment section. Salam and welcome everyone. So today we're going to be working on the question on the screen that says, estimate the internal pressure of water vapor at 1.00 bar and 400 kelvins, treating it as a van der Waals gas when the internal pressure is equal to A divided by Vm squared, by assuming that the molar volume can be predicted from the perfect gas equation. So as this question has a lot of words. As you can see, it's not a hard question. First of all, we're blessed with the fact that the equation that we're supposed to use to solve this question is already given to us, right? This here, this Vm right here represents molar volume, okay? For all of you who may need a little bit of a review. And this A right here simply represents the strength of attractive forces. So basically, we're dealing with the real gas here. But they told us that in order for us to determine the molar volume, we can use the perfect gas equation in order for us to simplify the problem. Meaning, even though it's a real gas, we're going to be using the ideal gas equation just to determine the molar volume. So what that looks like is for us to remember that Vm, okay, is the same thing as RT divided by P, right? So remember, PV equals nRT. Vn is the same thing as V divided by number of moles. So if you divide by number of moles and P on both sides, what you end up with is going to be Vm equals RT. So this is the equation that we're going to use to find the molar volume of the gas. Next, the best thing for us to do in order for us to continue this work is for us to determine the attractive forces value, which is A. Well, thankfully, this is a constant. So all you have to do is to look at the resource section of your book or go online and Google the A value, or the attractive forces or strength of attractive forces value for water vapor, and it is a constant. And since it wasn't given to us, please go online, Google it, or just look at the resource section of your physical chemistry textbook. And looking at the textbook, what I have is 5.464 dm6, okay, atm divided by mole squared. So having this information is very, very key. Now, we're also told, right, that the temperature is 400 kelvins and the pressure is 1 bar. But we have strength of attractive forces constant to be in ATM. So what this is telling you is that we have to go from bar, okay, to ATM. So if you're new to this channel, I've done unit conversion questions on for pressure. So if you want to learn how to do that in a more intense level, please watch that video. But I'm going to be doing that here just briefly. So we know that 1 ATM, okay, is actually equals to 1.01325 bar, okay? Hence, 1 bar is going to be equal to how many pressure? So all we have to do is just simply cross multiply. So what we end up with is, I'm going to be doing it right here. Let's continue here. There is space here. What we end up with one is 1.01325 bar, okay? P, and remember, we're cross multiplying, is the same thing as 1 atmosphere bar, okay? Of course, since we have same units on both sides of the equation, we can cancel this out, and we have actually pressure to now equal 1 atm, okay, divided by 1.01325. And when we do that, we determine pressure to be 1 divided by 1.0325 bar in our calculator. We end up getting 0.97402 atmosphere. So that's basically the pressure we're going to be using. So we know the pressure, okay? knowing the pressure and also knowing the temperature that we're given, as well as knowing the gas constant, which is a constant, we can successfully determine the molar volume. So, solving for the molar volume, we have RT divided by P. We know that R is just basically gas constant, so that's 0.08206 dm cubed atm divided by mole Kelvin, okay, times 400 Kelvin divided by 0.97402 atmospheres. So we're going to cancel out the atmosphere, cancel out the kelvins. So what we end up with is the molar volume is going to give you 0.08206 times 400 divided by 0.97402. And that, of course, is going to have the units dmq per mole. So we're going to put that in our calculator to get 33.6995 dm cubed per mole. So that's basically how you do it. Now let's go back to the question. We've been given the formula we're supposed to use for to determine we've given the formula that we're supposed to use in order for us to determine internal pressure. So we're just going to rewrite that here. We have internal pressure, okay, equals A divided by Vm squared. So internal pressure would look like this. A is just simply 5.464. Okay, looking back at what I showed you here. So A is 5.464 dm6 atm divided by mole squared. So dm6 or yeah, dm6 atm divided by mole squared. All of that information divided by 33.6995 dm cubed divided by mole, all squared. So, of course, we go on to do the math. So, we have 5.464 dm6 atm, okay, divided by mole squared, divided by 33.6995 dm cubed, divided by mole, all squared, is going to give you 1135.6563 dm6, okay, divided by mole squared. So basically that squared was there for us in order for us to properly cancel out the units and retain the unit of pressure, since we're just determining internal pressure. So dm6 cancels out, dm6 cancel out, mole square cancel out, mole squares cancel out. So 5.464 atm divided by 1135.6563 would give you the internal pressure of 0.0048113 atm. And of course, this is our answer. But the thing about chemistry is that we have to put things in the proper number of significant figures or decimal places. We see that we're given this question of bar in three sig figs, 300. I'm sorry. We see that we're given the pressure 1.00 bar in three sig figs and the temperature in 400 kelvins, which is also three sig figs. That means we have to put our answer in three sig figs. So really, the internal pressure, the answer for it is just simply 0.00481 atmospheres. So that is basically how you solve this question. So yeah, that's basically how it's done. If you have any questions, please put in the comment section. If you would want personalized tutoring, I am a tutor that helps students in high school, middle school, and college succeed in their STEM related courses, as well as in other aspects of their academic career. So if you like help in your class that you're struggling with, whether it's tutoring or mentorship, please email me at shohabitutoring@gmail.com. I wish you guys all the very best. Assalamu alaikum wa rahmatullahi wa barakatuh.